Hello dear students, we have got very interesting problem related to solubility product, ionic product, okay, and molarity equation. Okay, so what is given? An unknown concentration of barium 2 plus ion solution is given to you. Okay, now to that 1 molar solution of 50 ml of sodium sulfate is added. Total volume becomes 500 ml. Just precipitation takes place. Solubility product or ionic product is given because at this particular point, when the precipitation just begins, ionic product is equal to the solubility product. Later on, ionic product is going to exceed, thereby precipitation completes. So that is a concept. Now, what is that original concentration of barium 2 plus ion taken is to be calculated. Very interesting it is, okay. Remember, we are not given with the volume concentration of barium ion. Fine. So we have a basic formula, that is solubility product is equal to concentration of a barium 2 plus ion into concentration of sulfate ion. Is that fine? So solubility product, ionic product equal to solubility product when precipitation begins. Therefore we can substitute here same thing there. Okay, 1 into 10 to the power minus 10 can be substituted. Barium 2 plus ion concentration can be found out with this, but we are not knowing what is a sulfate ion concentration in 500 ml. That has to be calculated first. So to calculate SO4 2 minus concentration first, okay, let us consider M1V1 is equal to M2V2. Now this I'll take it as barium sulfate, okay, and this I'll take it as sodium sulfate, Na2SO4. Fine, no? So concentration we don't know, okay, I'm calculating sulfate concentration there. Therefore M1 into total volume will be 500 ml it is stored is equal to M2 sodium sulfate is 1 molar and its volume is 50 ml. So M1 equal to 50 by 500, which is nothing but 0.1 molar. We came to know what is sulfate concentration. Can't we find out barium concentration now? So equation 1 implies that concentration of barium 2 plus ion is equal to ionic product equal to solubility product when the precipitation begins. So 1 into 10 to the power of minus 10 divided by 0.1, which is nothing but 1 into 10 to the power of minus 9 molar. So barium 2 plus concentration when precipitation begins. So that's what I said, it is not the original or initial concentration, it is a concentration when precipitation begins. So how to calculate the original concentration? Again we have to go back to this formula, okay. So what is told there is barium 2 plus ion reacts with the Na2SO4, isn't it, to give barium sulfate. Why I am writing this? Because we don't know the volume of it, right? But this is 50 ml and this is total 500 ml. Therefore, what is the volume of barium, original volume? 450 ml. Am I right? Can't you find out now through this V1 M1 equal to V2 M2 formula? Because we know what is the volume of barium 2 plus ion. We know what is the volume of barium sulfate now along with the concentration. Can't we get this particular barium original concentration? Yes. So we will go for it. I'll write here to calculate original concentration, concentration. Fine, no? So we'll go for that. Concentration. Are you understanding, dear students? Yes. So what we supposed to do? V1 M1 equal to V2 M2. Fine. So I'm having 450 ml. Okay. V1 450 ml of it, and M1 I don't know. I have to calculate original solution. I have total volume of 500 ml and its concentration is 1 into 10 to the power minus 9. So 500 ml into 1 into 10 to the power of minus 9. So what is M1? M1 equal to 500 divided by 450 into 10 to the power of minus 9. How much it is? So 50 by 45 is cancels. Now 5 tens are 5 nines are 10 by 9, which is 1.1. So this is equal to almost 1.1 into 10 to the power of minus 9 molar. So this is a original concentration of barium. So which option, dear students? The option which is giving this value, as you can see, is option C. Okay, so option C to be selected. So that is the end of this problem. Hello dear students, we have got a sparingly soluble salt, that is aluminum hydroxide here. Its solubility to be found out. In what? Not in water, but in 0.2 molar sodium hydroxide. In water we know how to find it out. But what happens in 0.1 molar sodium hydroxide is, it will also supply that hydroxide 0.2 molar. It will also supply the hydroxide ion, right? As a result, hydroxide concentration increases. So common ion effect takes place. So solubility has to be decreased. So let us find out whether it is true. Now, what we do at the beginning is we write the solubility product expression for aluminum hydroxide. Okay, so AlOH thrice dissociates to give aluminum ion plus hydroxide ions. Okay, so 3 of them. These are in aqueous phase. Fine. So we have an expression for KSP. KSP is equal to what? Concentration of aluminum into concentration of hydroxide ion to the power 3. Now dear students, so being solid, aluminum hydroxide has got unity as the concentration. It's not changing. Whereas aluminum, we are taking solubility as S, and for this concentration as 3S, or solubility as 3S. Fine, no? Now, if it is water, directly would have been substituted because KSP is given. S can be found out. But what is given there is sodium hydroxide solution is taken to dissolve, which is a strong electrolyte, dissociates to give complete, right? Or dissociates completely. As a result, you are going to get 0.2 molar solution, will provide 0.2 molar solutions of both the ions. Am I right? Yes. So OH minus concentration is more, so that must be added. It is 3S plus 0.2 molar. Am I right? It's not having aluminum, so its solubility will be S itself. Here 3S plus 0.2. But there is a problem. This being a sparingly soluble salt, moreover, KSP value is very, very less. 2.4 into 10 to the power of minus 24. So such a low value clearly suggests that solubility is very less. So in comparison with the 0.2, this 3S can be neglected. So I'll write this is almost equal to 0.2 itself. Now S can be found out with the ease. So I'll write this as equation 1. Therefore, now 1 implies that KSP is 2.4 into 10 to the power of minus 24. That should be equal to aluminum ion concentration, which must be calculated now, into this concentration of hydroxide is 0.2, right? 0.2 to the power 3. Is that right? Yes. So what I'll do, I'll write aluminum ion concentration therefore is equal to 2.4 into 10 to the power of minus 24 divided by, I'll write this as a 2 into 10 to the power minus 1. So 2 cube and 10 to the power minus 1 cube. So 8 into 10 to the power of minus how much it is? Minus 3. Am I right? So 10 to the power minus 3. Is that okay? Now 8 ones are 8 3s are that, but here point is there, so 0.3s are. When it comes to numerator, 10 to the power plus 3. So plus 3 and minus 24 will be minus 21. But one decimal point I will extend this, so this will become minus 22. So the answer is 3 into 10 to the power of minus 22 molar. Which option to be selected, dear students? Yes, the right option, which is option C. Am I right? So option C is a right choice here. That's it. Hello dear students. the question is based on the molar solubility and solubility product. Okay, so it is a sparingly soluble salt, cadmium hydroxide, which dissociate to give cadmium and hydroxide ion. So as such, if it is asked, then directly KSP solubility product formula could have been applied and found out. Now the thing is that here pH of 12 buffer solution is used to dissolve this. What is the solubility? How to find out? pH indicates the H plus ion concentration, which in turn OH minus concentration. So OH minus concentration is not only due to cadmium hydroxide dissociation but also buffer solution. So that must be added, and finally solubility has to be calculated. Shall we do it? Yes. So what you do is write the dissociation, cadmium hydroxide dissociate to give cadmium ion Cd2 plus 2 OH minus ions. Am I right? So these are in aqueous state, whereas this is a solid. So let me write, see, molar solubility has got meaning only for the aqueous solutions. For this constant it is, or unity. So I'll write S as a solubility, this solubility has a 2S. Fine. Therefore I have a solubility product KSP is equal to concentration of cadmium 2 plus ion into concentration of OH minus ion the square. Let this be equation 1. Now I can substitute as such the solubility product of this to find out. Okay, KSP is equal to, see, this is S into this is 2S the whole square, so which is nothing but 4S cube. KSP is equal to, so substitute the solubility value. How much solubility is given? 4 into 1.84 into 10 to the power of minus 5 the whole cube. Fine. So when you solve for this, you will get the answer as 24.9 into 10 to the power of minus 15, and when you rearrange, you will get it as minus 15 as a solubility product. So 1.8, almost 2 cube. Okay, 1.8 cube into 4 will be 24.9 into 10 to the 4 minus 15. So this is the KSP value. What is asked? For this KSP value, what is the solubility in buffer solution of pH 12? So let us move on to that. Say pH equal to 12 implies that H plus concentration is equal to 10 to the power minus 12 molar. Right? Therefore, OH minus concentration should be equal to, I hope you know it is ionic product of water. Product of H plus and OH minus ion should be equal to, concentration should be equal to 10 to the minus 14. So minus 12 is from H plus. So OH from OH minus how much? Minus 2. 10 to the power minus 2 molar. So you came to know what is the OH minus concentration. So substitute in the equation. So when you have a pH of buffer 12, or right, buffer of pH 12, then it will supply OH minus concentration as 10 to the minus 2 molar. Then this 2S has got no value, right? It is very, very small because solubility product is there. Solubility is here, right? So therefore OH contribution is from mainly from or majorly from the buffer. So now solubility in a buffer of pH equal to 12, okay, is, how to find out? See, solubility product will remain constant because it's just an equilibrium constant. So equilibrium constant is a constant, right, depending on temperature. Therefore I can write KSP. So this equation I'm utilizing, okay, I'll write the molar solubility cadmium, concentration of cadmium 2 plus ion is equal to KSP divided by OH minus concentration the square. Fine, no? So I'll write here the further. So KSP value is just now we arrived, right? So CD2 plus concentration equal to, tell me, 24.9, right, into 10 to the power of minus 15 divided by what is OH minus 10 to the power minus 2 the whole square. So which is nothing but, see, 10 to the power minus 4 it is, when it comes to numerator plus 4. So it is 24.9 into 10 to the power minus 11 molar, or I will write this as a 2.49 into 10 to the power minus 10 molar, which is our molar solubility in a buffer of pH is 12. So as you can see, the option which must be selected over here is option D. Okay, that will be the end of this problem. Hello dear students, here pH of a salt is to be found out. Okay, that is ammonium chloride, which is a salt of weak base and strong acid, has got a concentration of 0.02 and its Kb value, that is Kb value of what? It is weak base, ammonium hydroxide is given 10 raised to minus 5. Fine. So we have a salt of for a salt of ammonium chloride, which is weak base and strong acid. For a salt of weak base and strong acid, pH is equal to 7 minus, how do you get 7? Half of pKw, which is 7 minus 1 by 2 into pKb plus log C. Okay, so this is a formula which is there to calculate pH of a weak base strong acid salt. Now pKb can be calculated because Kb is given, pKb equal to minus log Kb, log C is 0.02 concentration. So let us substitute 7 minus 1 by 2 into minus log of Kb, okay, plus log of C. So what I will do is I'll write this as 7 minus 1 by 2 into minus log of 10 to the power minus 5 substitution plus log of 0.02, I'll write as 2 into 10 to the power of minus 2. Am I right? Yes. So this is 7 minus 1 by 2 into 5. Here it is log 2 minus log 10 to the power minus 2 is minus 2, right? Plus log 2 is 0.3. Am I right? So 5 minus 2 is 3. 3 plus 0.3 is 3.3. 3.3 by 2 is 1.65. So this is 7 minus 1.65, which is equal to how much? 1.65. If you add 0.35, it will be 2. So 5 minus 2 is 5, 7 minus 2 is 5. 5.35. 5.35. So this is a pH of the weak base and strong acid salt ammonium chloride in 0.02 or having 0.02 molar solution. So which option to be selected, dear students, is the option C, which is a right answer. That's it. Hello dear students, here in this question it is told to calculate the solubility and solubility product relationship, okay, for zirconium phosphate sparingly soluble salt. Told that KSP is a solubility product considered and S as a solubility. Now how we can relate these two is the question. So what we do, we write an equation for the dissociation of zirconium phosphate, which is a sparingly soluble salt. What is the formula? It's given zirconium phosphate is PO4 3 minus, so zirconium 3 minus, zirconium 3 crossing the valency, okay, phosphate 3 minus, therefore 3 here, zirconium 4 plus charge or plus 4 charge, therefore phosphate. Am I right? So this is the formula. So now it dissociates to form zirconium 4 plus ion, how many? 3 plus 4 phosphate ion, 4 into PO4 3 minus. This is how the dissociation. Now as it is told in the question, we have to consider S as a solubility, right? So solubility we are not going to consider for the solid because it's unity. Next here it is 3S and here it is 4S. Now we know what is solubility product, right? KSP solubility product equal to concentration of zirconium ion raised to the power 3 because stoichiometric coefficient is 3, then phosphate ion PO4 3 minus, its power is 4. Am I right? Yes, denominator term is not there because it's a solid, so its solubility is constant. Now this is equal to Okay, zirconium, it's not zinc, zirconium, it is 3s to the power 3 into it is 4s to the power 4. Am I right? Yes. So now what you can write here is this 3 to the power 3. So 3 to the power 3 is, yes, tell me. 3 3 is a 9, 3 is a 27 into s to the power 3 into here 4 to the power 4, 4 into 4, 16, 16 into 4, 64, 64 into 4, 256. Am I right? So 256 into s to the power 4. So therefore totally 256 into 27, if you multiply, you will get as 6912 into s to the power 5. Sorry, 4 plus 3, 7 it will be. Okay. Now as a result, I can write solubility as solubility is equal to solubility product divided by, okay, hope you can see this, okay, KSP divided by 6912 whole to the power 1 by 7. So this will be your solubility product and solubility expression. So which option will give this answer, dear students? It is, yes, tell me, option B. Option B has to be selected in this case. That's it. Hello dear students, molar solubility of silver carbonate is asked. Am I right? Solubility product of it is given and its molar solubility to be calculated in 0.1 molar silver nitrate, which has got a common ion silver, remember. Okay, so what we do, we usually used to write this expression, isn't it? Silver carbonate dissociate to give silver ion Ag plus how many? 2 plus carbonate ion CO3 2 minus. What is given is KSP. It is equal to how much? 8 into 10 to the power of minus 12. Fine. Now silver nitrate is also given. So to the same solution we are adding silver nitrate, which furnishes Ag plus and NO3 minus ion. Now silver nitrate is of 0.1 molar. Being strong electrolyte, it will give 0.1 molar solutions of both the ions, or both the ions having 0.1 molar. Number of moles will be same. Now we usually write S as a solubility, here also S, so concentration is 2S. Am I right? Now what is given? Silver nitrate also furnishes silver ions, therefore the concentration is mainly influenced by silver nitrate solution, so 2S plus 0.1 molar. Since solubility is of the order of 10 to the power minus 12, which clearly says that solubility product is 10 to the power minus 12, so solubility will be very less. So in comparison with 0.1, 2s can be neglected. So this is almost equal to 0.1 itself. Now we apply the formula of solubility product. We have, okay, we have KSP is equal to concentration of silver ion, the square, into concentration of CO3 2 minus. Now this is nothing but 8 into 10 to the power minus 12 equal to Ag plus square is 0.1 now, right? So 0.1 the square into concentration of carbonate is S, later we will substitute. Okay, now this is nothing but S is equal to 8 into 10 raised to minus 12 by 0.1 square, which is 10 to the power minus 2. So S is equal to molar solubility, that is CO3 concentration. S is equal to, tell me, 8 into 10 to the power minus 12 divided by 0.1 is 10 to the power minus 2. So when it comes to numerator, plus 2, so it is 8 into 10 to the power of minus 10 molar is the molar solubility of silver carbonate in 0.1 molar silver nitrate solution. Which option to be selected? It is option C, okay, has got this answer, therefore it is a right answer. That's it. Hello dear students, yes, in this question we are given with the strong acid, sulfuric acid 20 ml 0.1 molar and the base, weak base combination, that is 30 ml of 0.2 molar. Now what is the pH of the solution to be found out? Now if it is a buffer forming solution, then we can find out with the help of Henderson equation, right? So if it's a basic buffer, pOH will be calculated first, then pH from that. Whereas if it is an acidic buffer, then directly. Acidic buffer it can't be, because acid is strong. Okay, for an acidic buffer, weak acid has to be. If at all it is there, then basic buffer. Let us find out by calculating the amounts of that. Later pKb is given, therefore we can compute it. So we'll write the equation: ammonium hydroxide NH4OH reacts with H2SO4 to form a salt. Okay, that is NH4. Okay, NH4 sulfate, ammonium sulfate is formed. NH4 twice it should be, right, plus H2O. This is a salt which is formed. Now it's given 30 ml of 0.2 molar, so millimoles will be 6 millimoles, whereas sulfuric acid 20 ml, right, 0.1 molar, that is equal to 2 millimoles. No product at the beginning. Okay, at equilibrium what happens, or at time t, okay, t minutes, what happens? 2 millimoles is going to get converted into salt. Why? This is a limiting reactant, isn't it? So product formed will be 2 millimoles, which is of weak base and strong acid salt. Fine. Now water concentration is not required there. What is remaining? Sulfuric acid remaining will be 0. We agree, because it's all sulfuric acid completed. Therefore the mixture contains a salt of weak base strong acid and excess of weak base. Therefore this is a basic buffer. Okay, so how much is remaining? 6 initially. Now sulfuric acid, okay, balancing here 2 moles. Am I right? So X, if it is dissociated, which X equal to 2, remaining is 6 minus 2 times the X, no? So 6 minus 4. Why it is? Because it's dibasic acid, that's it. Okay, so 1 mole will give 2 H plus ions. So 2 millimoles equal to 4 H plus ions, right? 4 millimoles. Therefore 6 minus 4, which is equal to 2. Is that okay? Therefore we have a Henderson equation: pOH equal to pKb plus log of concentration of ammonium, yes, sulfate divided by concentration of ammonium hydroxide. So now this is nothing, pKb is 4.7 plus log of 2 millimoles in total volume 50 ml, therefore 2 by 50, am I right? Milli will get cancels, so therefore 2 by 50 concentration divided by here also 2 divided by total volume will be 50, so this cancels, log 1 is 0, therefore pOH equal to 4.7. This implies pH is equal to 14 minus 4.7, which has to be how much? Isn't it 9.3? So 10 and 14 side, am I right? So this is nothing but 9.3 pH equal to, which is option D, students? Option A will give this answer, so that has to be selected. That's it.